Welcome to an Ultralight Airplane Design video from the Ultralight Airplane Workshop. In this video, we're doing another design video on the UWS-4 Ultralight airplane, and we're working on the aerodynamic design of the airplane. For the last few videos, we've been working on Part 11, which is covering load distribution on the wing of the Ultralight. We've gotten up to Part D, and in Part D, we're working on the chordwise distribution of lift on the wing. And in fact, you can see a demonstration of that down here in this picture, and we'll get a little bit more into the details of this picture here in a moment. As is our tradition on these videos, we're going to cover just real briefly what we covered in the last video. In the last video, we actually worked on the spar attachment point, where the outer wing panel is going to attach to the center panel of the wing. So we concentrated on figuring out the size of the bolt for that attachment in the upper spar cap and the lower spar cap. And we also figured out the height of the spar and the thickness right there where that bolt goes through and near that bolt. For most of this design series, we've been using a book from Dan Raymer called Simplified Aircraft Design for Homebuilders. But in this particular video, and some videos going forward, we're using a book by Chris Heintz, Flying on Your Own Wings. Now I do want to put in a little disclaimer here. This video is not a substitution for using Chris's book, just like the past videos haven't been a substitution for using Dan Raymer's book. Now if you might be interested in either of these books or some other books that I like, there's a link down in the description of this video that will take you to a web page of the Ultralight Airplane Workshop of books that I like, and there'll be links to Amazon, and if you use one of those links to buy a book, the channel will get a small cut of the proceeds. By the way, if you happen to find this video interesting, maybe you learned a little something from it, feel free to hit that like button. It'll help the channel a whole lot. Doesn't cost you a thing. Now you might ask, why do we care what the chord distribution of the load is for the wing? We need to know this chordwise load distribution so we can design the nose rib and the main rib and also the ailerons and flaps of our wing. We need to know how much shear those ribs need to carry, and we need to know the moment that those ribs are going to carry so we can design them properly. Now for the ailerons and flaps, specifically, we'll deal with those in another video. In this video, we're only going to work on the loads for the nose rib and the main rib. Now we said in previous videos that the span-wise distribution, how the load is distributed from the fuselage out to the tip, is largely dependent on the plan form of the wing, the shape of the wing as you look from above. It also depends on dihedral, and it depends on wing twist. But for the chordwise load distribution, that really depends on the angle of attack, the shape of the airfoil, how much the aileron is deflected, and how much the flap is deflected. Now getting these lift distributions isn't a simple thing. It's not overly hard, but it's not really simple either, at least to get accurate representations of that lift distribution. But there are some simplifications and approximations, and we're going to use one from Chris Heintz' book here in this video. Now I had intended to compare them to some calculations from XFLR5. That became a little bit problematic, so we're probably going to leave out the comparisons to XFLR5. But we will use XFLR5 to look at the distributions. So let me talk about what the goals are for this video. I want to get enough air load information on the nose and main ribs of the wing so that I can design them in another video. What I have here is a drawing that you may have seen before, but it has some more information on it now. I have some dimensions on here, for example, where the gap is between the aileron and the outer flap, and where the extent of the aileron is, the outer edge. And I also have some measurements on here where I think I'm going to have some ribs, or at least the spacing between the ribs. Now I only want to have one rib designed for the wing, so I don't have to make multiple kinds of ribs. So I'll design for the situation in here where the maximum load is. Now you'll find out when we get a little farther into the video, the ribs with the highest load are going to be here in the intersection, from the center out to just a little bit past where the boom is. The boom would be right in here. Now I don't yet know where the maximum load for the main rib is. Now it's the rib between the front spar and the rear spar. And I'll probably have to have at least two designs for that. I'll have a design for out here where these ribs are strictly taking an aerodynamic load, but there are some ribs that are going to take some extra load. For example, right here, this rib, it's going to take some extra load because there's a hinge here for the aileron and a hinge here for the flap. So there's going to be load concentrated on that main rib carrying shear load and moment load up to the spar. And the ribs right here where the boom attached, they'll have to have a little more load on them too, and probably in here near the fuselage. But most of these other ribs, the ones that don't have extra load on them, I want to pick whatever the worst case aerodynamic load is and design one rib for those. Now figuring out what that aerodynamic load is not going to be too bad. Once I figure out the aerodynamic load on the wing as far as foot per span goes, then I know that, for example, this rib will be carrying load halfway to the outer rib, the next outer rib, and halfway to the next inner rib. So from in here to in here, this rib will be carrying load that is going to be concentrated on the rib. Hopefully this drawing looks familiar to a lot of you. This is the flight envelope for the UWS-4 airplane. The highest aerodynamic loads we're generally going to have the wing are either here at condition A, which is our maneuvering speed, but at our N1 load factor of 3.8 Gs, or at condition D, which is our design dive speed at the same load. We also have another situation we want to be able to handle that we talked about in an earlier load factors video, and that's with ailerons deflected at 2/3 of N1. And we're going to look at that, where the ailerons are deflected 25 degrees at condition A and 8.5 degrees at condition D. Now 8.5 degrees is 1/3 of 25 degrees. I'm going to ignore this negative load factor down here, at least in this video. I'll probably go ahead and do it just to make sure there aren't some unusual issues that pop up. But it's just going to be the same procedure we're going to do up here at top. It's just that the load factor is just a little over 1.5 negative. And we're going to save flaps for a future video. Let's revisit the span-wise load on the wing. This kind of turquoise or light blue line up here, this thin one, this is at our condition A at our N1 load factor. Now we saw this on a previous video. So in here on this intersection of the wing, we have roughly 100 pounds per span foot. So this is 7 foot across here. So we have a lift from here to here of about 700 pounds. But this diagram is also showing load factor for our maneuvering speed at 2/3 of N1 and at our dive speed at 2/3 of N1. And that's this blue line and green line here. In addition, I've deflected the ailerons and looked at load factor also. So this red line is at the dive speed with ailerons deflected. So that's at 25 degrees deflection. And then this purple line is at the dive speed, but with 1/3 deflection. So you can see the worst case load out here is at our dive speed with 1/3 deflection. Now up here on this center section, I'm pretty sure that it's the nose, the part of the rib that's in front of our spar, is going to have a higher load on it than it will out in this area. And I suspect that the main rib is going to have a higher load on it when this aileron is deflected. So what we're going to do in this video is look at those loads up here in this condition and this condition and see if I'm right and see what those loads are so that we can design our ribs. Now we're going to figure out those aerodynamic loads along the chord using a pressure distribution. And that's what we're looking at here. This is produced by a program called XFLR5, and these arrows are pressure. The longer the arrow, the more difference in pressure from the ambient pressure, or the pressure out in the free stream. Now if the arrow is pointing away from the airfoil, that means the pressure is less than free stream pressure. If it's pointing toward the airfoil, that means the pressure is greater than the free stream pressure. Now these lines up here are just a graph representation of the length of these lines. The one on top here represents the top airfoil. Something you can't quite see is that these are actually negative numbers up here because the pressure here on the top is less than the free stream pressure. And then down here is positive numbers, and these numbers right here on this leading edge, these are positive numbers, so that's why they're down here. What we are interested in is the difference in pressure between the top and the bottom. And so all you need to do is look at the distance between the top line and the bottom line. And you can see in this particular situation, this is at our dive speed for the airfoil on our airplane. We have a Reynolds number of 5.2. The coefficient of lift is roughly 1/2, and the coefficient of moment is minus 0.035. Now you can see, looking at this difference, this is pretty much triangular shaped. And there are some approximations for lift distribution on an airfoil, or pressure distribution, that actually use a triangular shape like this. Ours is going to be just a little more involved because this triangle shape isn't quite adequate, at least for not what we want to do. Now I mentioned before that the pressure distribution can change with angle of attack. Let's take a look at that. So here's the same airfoil, but at a much higher angle of attack. In fact, it's the stall angle. And you can see now that these lines got much, much longer, and they're concentrated up toward the front. You can also see we're still somewhat triangular shape, but now there's quite a little dip in here. So if you wanted to approximate it, you can actually cut it up into several sections, and that's actually what we're going to do here in a minute. But in this video, we're not going to use XFLR5 for our pressure distributions. We're going to use an estimation from Chris's book. But I want to show this to you so you can see what they kind of look like a little bit closer to real life than the approximation we're going to use. Now let's talk about how those forces are going to affect our ribs that we want to design. So again, roughly here is where our spar is going to be. There's going to be lift on the nose rib. There's going to be lift on the main rib. Here is where our rear spar is. And then of course we're going to have lift from our ailerons and flaps back here. So here at the spar where our ribs are going to attach, these ribs have to transfer all that lift to the spar. So we need to design the main rib to handle all of the lift here between the spars, plus it has to take the aileron lift and move that forward also to the spar. And then again, likewise, the nose rib, all the lift that it's seeing has to be transferred to the spar. So we're going to have shear action here between the ribs and the spar, and whatever means we use to do the attachment has to transfer that shear from our ribs to the spar. But we're also going to have moment. We got lift out here that's not at the spar, it's in front of the spar or it's after the spar. So that means we have a moment arm there. And so that lift combined with the moment arm is going to create compression forces normally here on the top and tension forces on the bottom, at least if we're pulling positive G's. So we're going to have to design this area here to handle that moment and here to handle that moment. So again, that's why we need to know these pressure distributions, the lift distribution, or more accurately, the normal force distribution. In this case, normal to where we have the spar right here. Now let's talk about some of the overall forces. Let's get some actual numbers here. So 2/3 of N1 is going to be 1,310 pounds. The full N1 is going to be 1,965. This matches what we've had in the previous video when we were working on our N1. And we're going to work at our design maneuvering speeds and our design dive speeds. And the dynamic pressure that we get at those is about 10.5 and 30.7. And that's in imperial units. Now I want to know what the overall coefficient of the wing is going to be in these conditions. And I used our lift equation to do that calculation. Now I'm using 517 pounds as our weight. And then we have the load factor, 2/3 of N1. We have 121 square feet for our wing. So I do those calculations, and for these 4 conditions here, I know what the coefficient of lift of the wing is. Now remember, a big L means the wing, a small l means the section or an airfoil section lift coefficient. Now at our maximum lift, the section coefficient is going to be about 90% of our whole wing lift coefficient as a really rough approximation. All right, so that kind of gives us the overall behavior of the wing. Well, now let's see if we can do some approximations for how that lift is distributed on the wing, or in our case, that normal force on the wing. Well, I've borrowed something from Chris Heintz' book, the book we just talked about, and this describes the approximation that he's giving us to try to come up with that distribution. There's 2 major components to it. There's a pressure sub 1 and a pressure sub 2. Now, what we can do is calculate the pressure at any x from the leading edge, which is over here, to the trailing edge over here. And x would be 0 and then 1. So that's what this equation here is. So Q, dynamic pressure, which we just looked at. P sub 1 at some x. So that's from this graph. So we multiply that by coefficient lift. Now we have to be a little bit careful here. I used a lowercase l subscript, which is normally for a section coefficient lift, but it's really the coefficient lift at the particular location along the span we're interested in. So let's go back to this diagram. Here is along the span. We want to figure out the distribution, let's say out here on the aileron. So we're really interested in what the coefficient lift is right out here at this particular location, not the whole wing, and not necessarily the sectional coefficient lift, because that won't necessarily be the same either. We have to come up with some way of estimating what the wing coefficient lift is at some position along the span. So that's what this coefficient lift is. And then the second pressure, P sub 2, is from this diagram down here. And you multiply it by your coefficient of moment measured at the quarter chord. Now this second one down here takes into account your flaps or your ailerons being deployed. And that modifies this coefficient of moment. So for flaps, let's ignore that. We're only really dealing with ailerons in this video, or at least how the deflected ailerons affect the distribution for the nose and the main rib, and they do. So for deflected ailerons, for each degree of deflection, you change that coefficient of moment by 0.01. So if your trailing edge of your flap goes down, it's negative. If your trailing edge goes up, it's positive. And this delta means how much you're going to change the coefficient of moment. And by the way, this E, that is the span of your flap or your aileron. Now for us, it's 0.25. Now I use the spreadsheet to do these calculations because doing them by hand would be very error prone. I took the results of those graphs and I did a little drawing here. So this is using Chris's estimation we just looked at to look at the chordwise distribution. So now let's talk about what we're seeing here on units for this vertical axis. This is the chordwise lift distribution in pounds per square foot. So this would be our leading edge here. Here's our trailing edge. So I wanted to give a comparison here of our N1 condition and 2/3 of the N1 condition at our VA speed and our VD speed. So that's what these 4 lines are for. So these top 2 are N1. These bottom 2 are at 2/3 of N1. The green line here is our maneuvering speed, V sub A. The purple line is our dive speed, V sub D. So you can see when we're at V sub A, we have a much higher angle of attack that moves the lift forward toward the nose. That's why this is higher here. But you can see down here, it's lower. Because when our dive speed, we don't have to have as much angle of attack to produce the same lift. And that's going to end up moving lift a little bit farther aft. So away from the nose and a little bit farther back. So that's why the purple line is higher than green line here, but it's the other way around here. That's just because the angle of attack change. So there's no aileron deflection here. Now these next 2 lines are at 2/3 of N1. And you're seeing the same thing. The red line is V sub A, the higher angle of attack. The blue line is our dive speed, a lower angle of attack. So you're seeing the same exact thing here. So at a higher angle of attack, our lift is moved more toward the nose. At a lower angle of attack, it's moved a little bit back from the nose and more toward the center of the wing. So the blue line's higher here, red line's higher here. So here at the center of the airplane, these numbers seem to be pretty correct. This condition is going to apply for the nose rib and the main rib from the fuselage out to almost to where the aileron is. So from the center out to, probably out to about here. So the center line out to about out here. I think we can design our nose rib and main rib using these numbers. So let's see what that's going to be. So adding from the nose out here to 30%, that'll give us the forces on the nose rib. And from 30% to 75%, where the aft spar is, that'll give us our main rib numbers. So that's what I've done here in this little table. This row here represents our V sub A speed. Now this is at N sub 1, our 3.8 load factor. This is our design dive speed, again at 3.8. So we need to design those ribs to handle the loads in these conditions. So the nose rib lift is going to be 60 pounds per span foot. The main rib lift for our V sub A speed at N equals 3.8 is 28.5, and we'll ignore the aileron lift for now. In fact, it would be a flap lift on the area we're talking about. And the moment for the nose rib, that's 11.5 in the negative direction. And it's negative because it's in front of the spar. Positive would be behind the spar. And the main rib doesn't have a huge moment, at least not compared to the nose rib. So that's kind of interesting. Now, let's look at our design dive speed. In this case, the nose rib lift is less at our dive speed, but the main rib is more, and that's what we just looked at here in our drawing. At our maneuvering speed, we should have a greater lift on the nose. At our dive speed, though, is when we'll have a greater lift on the main rib in this area. So our numbers, at least relative to each other, make sense. So that's what these green numbers are here. That's where the maximum force is. And moment corresponds to the same thing, of course. We have a greater moment on our nose at the maneuvering speed and a greater moment on the main rib at our dive speed. Now once we add in the flaps in their neutral position, that's going to add a little bit more load to the main rib. So we'll have to take that into account too. For anyone that would like to do something similar to what I did in the spreadsheet, I'm going to give you a quick overview of what I did. Up in this area, I've captured the various values that are going to go into our equation, at least the fixed values. So it's going to be like our chord, the chord of our control surface, like our aileron or flap. Now E is going to be how much percentage that our control surface is of our chord. So that's 0.25, 25%. I got our angle of attack. That's not actually used in the equation. That's just to kind of keep track of what's what here. Got the coefficient of lift, coefficient of moment, the angle of our flap, which could also be an aileron, and then our Q value, our dynamic pressure. Over here on the left, I have the X's. I've kind of arbitrarily selected some X's. They're kind of wide here on the back end, and you can actually see how wide apart they are here in this delta X column. And then as they move forward, they get closer and closer together. And at the nose, they're pretty close together. So 0 is at the nose, and 1 is at the trailing edge. So the first thing I calculate is the P1, and that is the pressure that we're going to multiply by the coefficient of lift. Next is P2, and we'll multiply that by our coefficient of moment. And then I go ahead and do the whole equation here in this column. So I do what I said here, multiply by the coefficient of lift, multiply by the coefficient of moment, add those two together, and then multiply by our dynamic pressure. So these are the values here, and these are the values that I put into the plots. So these values are basically giving us a pressure per square foot, because the units that we used for Q up here. But now I want to start getting into pressure per span foot. So I take our pressure per square foot and I multiply by our delta X. Now this is still 0 to 1. It's not including our chord yet. And then down here, I sum all those up. That gives us an average of what I'm calling pounds per span chord. Now if we multiply this by our chord, which is a little over 5 foot, that gives us our lift per foot span. So we multiply by some span portion, that'll give us a total lift for that span. And so here in this particular example, we have a lift of 93 pounds per foot span. And that matches fairly closely with what we have calculated before for the center portion of our span. And there we got in the high 90s. So we're within about 5% or so. And then down here, I subdivided it into the lift per foot span for the aileron, the main rib, and the nose rib. But I also want to get the moment, particularly at the spar. So I figured out what the moment arm was. This is in values from 0 to 1. You have to multiply this by the chord to figure out where it is from the leading edge. So you can see the moment for the aileron is about 83% of the chord. The main rib is at about 50% of the chord. And the nose rib is about 11% of the chord. And that's from the leading edge. And then you multiply this by this, and that gives you the moment. And that's really all there is to it. Let's wrap up talking about the nose rib. Now I know what the pounds per span foot load is on the nose rib. I can figure out what the total load is going to be on that nose rib. So let's say we want to calculate the load on the rib here. And by the way, I'll probably use the same exact rib throughout the airplane. I'll only really need to design it once. So let's say this is the rib we want to work on. So the load for this rib is going to be halfway from the inboard rib and then halfway to the outboard rib. So this area right in here, well, that's going to be 14.8 inches. So I convert that to feet, multiply by my pounds per foot span, and that gives me the total load on that rib. And then from that, we can calculate our moment, and we can go back for each location where we're going to put a rivet, and we can calculate what the load is going to be on each rivet on that nose rib. So we have enough information now to go and design our nose rib, and we'll do that in a future video, here in the not too distant future. Now let's go back and look at what our aileron deflection is going to do to our loads out here on this area where the aileron is. Let's go back and look at Chris's equation for estimating the load along the chord. Now I mentioned before that that coefficient of lift is the local coefficient of lift, and by that I mean the coefficient of lift out here at some spot along the span. Now we're interested in our ailerons now, so that's going to be somewhere between here and here. Now for Chris's equation, we want to know the lift when we're not deflecting the ailerons. So that's actually going to be the lift down in this area on this green or blue line. And that's also going to be the coefficient of moment down here on this green or blue line. So once we know that coefficient of moment down there without the ailerons deflected, then we'll add in the delta that we talked about. So we know that our condition is at 2/3 of N1, and we know that this purple line is our dive speed. So that's the condition we're going to look at here. That's our worst case condition for the ailerons. So we're going to start here in the middle, and we're calling that position wing station 0. Now just looking at this graph, we can see that our amplitude here for our loading is at 65. And we know out here at wing station 9, which is 9 feet out from the center. Now in the future, when I talk about wing stations, we'll actually be using inches, but just for this calculation, since most of our units in feet, we'll just be calling them feet for now. So I think that I'm going to use 9 feet out here for our calculations. And that's really just to kind of get us going. What I'd rather do is figure out what the average lift is when we're deflected and use the center of that. But I haven't done that calculation yet. So let's just say 9 feet. It's probably a little higher than what the average is, but it'll work out for us. So we're going to come down to our green and blue line and figure out what our lift is here. So down here, we can see that it's about 49. And just for grins, I did some calculations here for when it's deflected up and when it's deflected down. And I grabbed those numbers too. Well, now in order to figure out what the coefficient of lift is out here, I'll take the ratio of our lift at the wing station 0 and lift out here at wing station 9. And that ratio is 0.75, so about 75%. So that means our coefficient of lift out here should be 75% of our center wing lift coefficient. So now we just need to figure out what that center wing lift coefficient is. And that is essentially our section coefficient of lift for our airfoil. Well, we've already figured that out. It's 0.395. So I take this 0.395, multiply by our 70%, and we get a lift coefficient out here then at wing station 9 of 0.298. But that's without the ailerons deflected. So let's look at that case. So at our wing station 9, this is our lift with the ailerons deflected. In this case, it's 8.5 degrees at our dive speed. So what's the ratio between here and here? Well, this value out here is 77.5. We do our ratio here, we get 1.19. So now we multiply the coefficient of lift here we had at the center by 1.19. And that's what we do right here. And that gives us 0.470. So our coefficient of lift out here is 0.470. And then I do the same thing for the coefficient of moment. I figure out what the coefficient of moment was for our airfoil. It's minus 0.039, and that's at this condition here, 2/3 of N1 VD. And then multiply that by our 0.75, and we get the minus 0.262. But what about the coefficient of moment up here with the ailerons deflected? We're not going to do the same thing that we did for coefficient of lift. We're going to keep this coefficient of moment that we got down here without the ailerons deflected. And then we will add in the delta that we get from Chris's equations. So now I can plug that coefficient of lift in, coefficient of moment in, and get Chris's graph out here for our undeflected airfoil, and then we can add in the deflections. Well, again, here's a graph of a chordwise distribution of our pressure, or our lift, however you want to think about it. But this time we've included the ailerons being deflected. Now I've still got the original two graphs we have here at our maneuvering speed and our dive speed. And we use this one, this green one, for our nose. Now for our blue lines, these are out here at our aileron, at the wing station 9. The thick one is without the ailerons deflected. So we can see we have a lot less lift out there since our coefficient of lift is way less. So that doesn't have any impact on our nose design. And it's quite a bit less here for the main rib, so it doesn't have any impact on that either. Now this thin line up here, this is with the aileron deflected down 8.5 degrees. This lower line is with the aileron deflected up 8.5 degrees. So we have more lift when we're deflected down and way less lift when we're deflected up. And that's what we should expect. Well, as you can see out here, right here is our hinge line for our aileron. We have way more lift when the aileron is deflected down here at our dive speed at 2/3 of our N1. So we're going to need to design our aileron to this condition here. Now look here at our main rib. If you look at the total area underneath from here where our spar is to our hinge, when this aileron is deflected, our main rib has more force on it than our other two conditions we looked at. So we're going to have to design our rib to handle this condition here with the aileron deflected at our dive speed at 2/3 of N1. Let's look at the aileron deflected up where we have less lift. Now if we design our aileron to be symmetric so it can handle both the same positive and negative loads, this aileron deflected down won't be an issue, because if we make it symmetric, it'll be able to handle a load way down into here. Basically this line mirrored underneath. Now, assuming I use the same main rib throughout the wing, we now have enough information to design our main rib, although we do have a couple of exceptions. Now, looking at this in numbers, you can see that the pounds per span foot, again, for the nose, we looked at this before, 60 pounds per span foot. And like we looked into the graph, the lift due to having the aileron deflected is quite a bit less than that. So we're still sticking with our V sub A condition at N equals 3.8 for that. Our main rib, as we said before, the lift increased on that main rib because we deflected the aileron is quite a bit. It's up to 42 pounds per span foot. And for the aileron, it's quite a bit more. Now, I didn't mark this in green because we're actually going to do another video on the aileron by itself. There's another way to estimate it using part 23, and we're going to compare that to what we came up with here and see what we learn. And again, the moment on that main rib is quite a bit more than in the VA at N equal 3.8 condition. But again, that moment and this lift over here doesn't include the contribution due to the aileron acting on its hinge at the rear spar where that main rib is. So we'll have to include that too. Now we have enough information to not only design our nose rib, but our main rib too. So what's the next video going to be here on our aerodynamic design series on the UWS-4? Well, as I just mentioned, we need to work on the ailerons deflected and we need to work on the flaps deflected. I want to know what the loads are going to be on the ailerons and on the flaps. Now, probably won't be the next video to actually come out on the channel. That'll be next when we do on the aerodynamic design. We're going to do a structural video, I think, next. First, we'll look at a nose rib and a main rib, kind of similar in idea to what I want to do on the UWS-4. And that's going to be the nose rib and main rib for the Ultra Cruiser airplane. I've got some of those, and we'll talk about the design features for those ribs. And then I think the next video following that in the structural design series will be an actual design for the nose rib. And then I think we're going to build one and test it. Well, guys, thanks for watching. Until next time.